Yeah, thank you for the introduction. So to correct this, I'm a PhD student, but never mind. So you had the titles. Only one remark in the beginning. If you're working a lot with hydrogen, do a lot of tests with hydrogen, then many things might not be that new for you. But we still get a lot of questions on which methods can we use to test materials, especially steels, with hydrogen. And therefore, we wanted to address a few of these questions. So I would want to start with a short motivation and then go into the first topic, which is the comparison of different ex situ methods, only tensile tests in this case. Then I go to the in situ methods, which one exists. And then I want to compare these in situ methods with ex situ methods. And of course, I will end with the conclusions. So to the motivation, as you all know, the plan is to have an energy transition. Therefore, we have to test a lot of materials. And yeah, on the susceptibility to hydrogen embrittlement. And as you know, we always make a few simplifications if we test materials. So we don't test the whole pipe usually, but for example, if we want to know the materials behavior of a pipe of steel, then we don't test. Yeah. And then we usually take a smaller specimen, for example. This is the first simplification. We have another geometry, and we also have other simplifications. And this is what I want to focus on. Maybe a few general things. So one simplification could be that we take, instead of gaseous hydrogen in an in situ test, maybe we could do an ex situ test. So we pre-charge the specimen. And a second simplification could be that we, instead of gaseous hydrogen, for example, use electrochemical charging. Okay, perfect. So as I mentioned, first the ex situ methods, we can use electrochemical charging. As I said, that's an additional simplification. It's an easy method. That's why many people do this. It's applicable in many labs, and you get quick results. And you also have some benefits that, for example, you can transfer the specimens very fast to the test. But you have some problems. For example, if you test an austenitic steel, usually you don't get a uniform distribution of hydrogen in the material. I will go to this later. And you can as well do gaseous hydrogen pre-charging. This is for this you need an autoclave, which means higher costs, especially for safety equipment. And but this has some benefits, especially for austenitic steels, which I study. You get a uniform distribution of hydrogen with the right parameters, of course. And but you also have some downsides, for example, that you usually have a higher transfer time from from pre-charging to the test. But for the austenitic steels, that's not really important. This was the wrong direction. Okay, to the methods for the first experiments. So we pre-charged specimens, usual tensile specimens. First, we pre-charged them electrochemically with the solution you can see there. And secondly, we pre-charged them using gaseous hydrogen in an autoclave. And then we got out the samples, put them into liquid nitrogen, and did the test afterwards. Of course, we brought them back to room temperature again. All of this was a usual tensile test, so no slow strain rate, but 1 millimeter per minute, the cross-head speed. And we got a more or less comparable amount of hydrogen in this specimen. So here you can see the results. The black curve is the reference. The blue curve is pre-charged with gaseous hydrogen, and the red one is electrochemically pre-charged. So if you only look on these curves, you see, okay, we have an effect with electrochemical precharging, but we do not really have an effect, so that's not significant with the gaseous precharging. Okay, but if we look into the fracture surface, we see that the reduction of area, which was mentioned before, is very different. So you see here always the diameter of the specimen. So the reduction of area is much higher in the reference than in the electrochemically precharged, which makes sense. And what is also the case is that in the gaseous precharged specimen, the reduction of area is also lower. This means the reduction of area shows an effect of hydrogen for both methods, while the elongation at fracture does not show the influence of hydrogen in case of the gaseous precharging. Why is this the case? So here we see an electrochemically precharged specimen. We see in the middle, so there's only a part of the specimen. In the middle, we have a very ductile part where the material is not really affected. And on the outer wall, we see that it's a more brittle failure. So we have these two regions. Can also see this in an overview here. So this is more or less all over the specimen. We have a ring of approximately 100 microns, which are affected by hydrogen, and the middle is not, there's no visible effect of hydrogen. This is, why is this the case? This is mainly because we don't get any hydrogen in the inside of the specimen. If we do a short simulation, then we see of the hydrogen concentration after the precharging. You see on the border we have some hydrogen, but in the middle, so the simulation shows no hydrogen. And this, of course, explains the difference to the gaseous precharging, where the hydrogen is spread all over the material. But of course, the local hydrogen is concentration on the outer surface is much lower. Okay, to the second part, the in situ methods. There are different methods. For example, there is the electrochemical charging in situ during the test. I will not go into this. There is also the gaseous charging during the test in an autoclave. That's the conventional method. And what you also hear is, sorry, this is the wrong picture, is the in situ gaseous charging using hollow specimens. And there are a few differences. So with the autoclave, usually you have very high costs, especially for the safety equipment. But it's a standardized method, and it's more or less close to real-world scenarios compared to some other methods. With the hollow specimens, we have the advantage that it's much cheaper. It's easier to apply in a lab because the amount of hydrogen used is much lower. And it's, you could say it's also close to real-world scenarios. This is the hollow specimen we use. So this is the shape of the specimen. We put gaseous hydrogen inside the specimen, and then we do the test at different strain rates. In this case, what I show a bit later, it's 10 to the -6 1 per second. But one disadvantage is that this method is not yet standardized. But what I have to say there, this is something which is where we see some progress. So there are some projects focusing on this to get really this method standardized in the future. So here some images of the setup. You fill in the hydrogen and you have this applied to your standard slow strain rate tensile machine. Okay, I said I want to compare two things, the ex situ tests and the in situ tests. Therefore, we pre-charged some hollow specimens. and tested them, and we tested some hollow specimens in situ, which were not pre-charged. For the in situ tests, we used 100 bar of hydrogen. We did all the tests at room temperature. And for the ex situ tests, we first pre-charged the specimens at 100 bar and 300 degrees C for approximately 3 weeks. Yeah, and there we used another reference because at the 300 degree over 3 weeks, the materials properties might change a little bit, and they do. So what we can see here is in black, the ex situ tests, in red, the in situ tests. And I think there's, we clearly see that there is definitely a difference. So the ex situ test in this case shows an impact of the hydrogen, but it's not that big, while the in situ tests show much more effect of hydrogen. If you do the same as before, also look into the reduction of area, we see that there we have more or less the same. So you see the diagrams here. This is the embrittlement index based on the reduction of area and based on the elongation at fracture. And in both cases, we see that for the ex situ test, we have a lower effect of hydrogen compared to the in situ tests in red. Okay, and with this, I come to the conclusions. So as we have seen, the results we gain by ex situ tests are not directly comparable to these gained by in situ tests. The same is true for the tests with electrochemical charging compared to gaseous charging, at least in this case, where we don't get a fully saturated material or uniform distribution. Yeah, for many real world scenarios, I would say the ex situ tests are not really what we want to do because, first of all, they are not the more conservative ones. And secondly, if you think about a pipeline, for example, you could argue that there might be some kind of a pre-charging, but the more important thing is that we have gaseous hydrogen available while the load is applied. Yeah, depending on the application, you could also think about doing pre-charging and then do the in situ test. That's just to be even more conservative. Yeah, and one last thing about the hollow specimens, they can be used to have a cost-effective method, which gives us in situ tests. Of course, we also have some simplifications there. But this might make more sense than doing tests with electrochemical charging or pre-charging or something. So we still have simplifications. We still have to think about how we can transfer this to the real world. But it's at least closer than the pre-charging and especially the electrochemical pre-charging. Yeah, with this, thank you very much for your attention.